Okay, that was The Doors with Jim Morrison, and the selection, Ernie tells me, would have gone on for a few more minutes. It's 7+. What was the selection of that?
L.A. Woman.
L.A. Woman. Oh, I guess I want you to be at page 597 for a moment.
On 97?
597. And we're going to go to the document cam. This is a summary of what I was saying yesterday, and I thought it was a good place to start. So we go to the document cam, and it just talks about the methods. It's a summary of the methods we can use to solve a quadratic equation. And they're really listed in some respects as to the order of perceived difficulty. So the first one, which is factoring, the argument is usually the fastest method. And I'll just read what, because I don't want to scroll across. The disadvantage is given here as not all equations can be solved by factoring. And of course that's clearly the case. And some factorable polynomials are indeed difficult to do. So if you can't see the factors, it's not an effective technique, obviously. Let's go to the second. Coming back. The square root property. I mean, clearly, if you have something in the form, and they give it to you there as something squared equals a number, and the understanding is that the a number on the right side is positive, and it's really nice when it's perfect square, that's a neat way of doing it. But coming off there, the disadvantage, few equations are given in this form. I mean, it's a nice little technique if somebody's kind to you. But realistically, the number of times you're going to see an equation in this form, pretty darn seldom. Coming back to the third technique, completing the square. It can always be used. And the point, it's useful in other areas of mathematics. We talked about that yesterday. I'm going to come back to that briefly. But let's go to the disadvantages as we come off there. It requires more steps than other methods. It's a lot of work. So that brings us to the sort of sledgehammer approach. If you're breaking a rock, pounding a nail in the wall, it'll always work. It's just sometimes more than you need. But let's go to step 4 there, quadratic formula. It can always be used. And then, of course, the difficulty as a disadvantage is it is more difficult than factoring because we have the square root of b squared minus 4ac. And that is just perhaps a little more intimidating, just in its structure. And that gives you the methods that we talk about. Now, I do have a couple problems that have been requested on email as far as covering questions from homework. Before we do that, I'd like to review something we did yesterday just as an effort to keep it in front of you for a couple days. We talked about a circle. X squared plus y squared equals r squared. And I gave you an example of where we could use completing the square to locate the new center or origin of that circle. So let me write on the board the equation we talked about yesterday. X squared plus y squared is equal to r squared. Now the argument here, this has a center at the origin. And the radius is r. Now, if I can write the equation in this form, x minus h quantity squared plus y minus k quantity squared is equal to r squared, then I know it's a circle that has been relocated. It has been moved. Has the same radius, but its center will have moved a certain distance to a new point. I'm going to give you an equation, a little less easy than the one we had yesterday. Remember yesterday's was x squared minus 2x and y squared minus 2y. That made it a little bit too easy. Let me give you something a little more challenging. So x squared minus 6x plus y squared minus 4y. And then I'm going to have that equal to something, and I have to do a little bit of work in my head for the moment to come up with a nice number. But I think I'm going to go ahead and make this 38. Now my question. I want you to rewrite this in the following form, and then I want you to fill in the missing space. So I'm going to put a blank there. Then plus y squared minus 4y plus another blank. And then this is equal to 38 plus blank plus blank. So you're going to fill in the two blanks over here to finish it off. So we're going to complete the square in x, complete the square in y, and whatever we added on the left side, we add on the right side, so I can get it in the form ultimately of x minus something squared plus y, having trouble with that plus sign again, plus y minus something squared, and then I want that equal to
38.
something squared. So that's the goal. So we'll give you a moment to work with that. See if you can come up with the appropriate numbers I'm going to add. We want to complete the square. The key, by the way, take the coefficient of x, divide it by 2, and square it. Take the coefficient of y, divide it by 2, and square it. That's the argument. And then, of course, what I want to know is what is the new center? So the center of this circle, the place where we would start creating the circle, is going to have some pair associated with it. And if you can give me that pair, I'll know if you have the right number. Okay, somebody want to give me the ordered pair where the new center is going to be.
3, 2.
Okay, a 3 and a 2. Anybody agree?
No, we
Got
don't agree.
2, 3, 4 agreements. Okay, let's see if it works. I'm going to come back to the 6. That's the coefficient of x, so what do I do with the 6? Divide it by 2, that's negative 3. Square it, that's 9, so I'm going to add 9 there. That means I can write that trinomial as x minus 3 quantity squared. So h indeed is 3, so that's good. Okay, I had negative 4y, so I divide the 4 by 2. That gives me a 2. Square that, and I didn't do a good choice here. Bad move on my part. What I should have done,
We're changing it now.
I'm going to change the number here, 36. Sorry about that.
Thank you.
Okay, now, because I wanted something squared, and it was going to be difficult with the number I had. This is y minus 2 squared. Gives me y squared minus 4y plus 4. Now, I added a 9 here and a 4 here, so I'm going to add a 9 and a 4, and that's going to give me
49.
49, which is 7 squared. So I know that this circle is centered at at 3, 2 with r. I'm going to put and r is equal to 7. So you have a circle with its center and its radius, and you could draw the circle for me. Now that's called translating axes. Because in essence what we've done is relocated my circle so that its center is in a different location. So let me come up here and sketch what we've done. So I want you to get a little better idea of what we're talking about. Now, in the original problem, x squared plus y squared equals r squared. The argument is your center is here at the origin, and you can just draw a circle with radius r. We call that standard form. So this would be standard form for a circle. In essence, what I've done by this completing the square is said, let's come over 3. Let me see if I can get that drawn carefully enough. There's going to be 1, 2, 3, and then up 2. So I'm going to just dash in a line here that's up 2 and over 3. So we have relocated this as the center of the circle with a radius of 7. Now that's going to be a little bit tough for me to go ahead and do as a circle without a compass. But the idea is that I would then have to come out 7 units way out here. See what I can do to create somewhat. Oh, I'm in trouble.
It's a pretty big circle you've got there.
Okay, let's come down here. This is an effort to create what would be a circle. Well, something like this, and I'm sliding in a little bit. But I would have a circle then coming up through here, and that would be in standard form now relative to what? To this new center. So what we sometimes do is call this a new axis, and this a new axis. And then we argue that the equation relative to the new axis is going to be what? New equation now would be big X squared plus big Y squared, and that's equal to 49. Now we refer to this as a translation. So what we've done is translate the original center for a circle to a new location, 3, 2. So we just have created a new axis system that's over 3 up 2. And relative to that new system, I have my equation in standard form. That is a tremendously important process. Any questions there?
This is done in Math 90, right?
Oh, it's done in
It's-
90, it's done in 121, 122, calculus sequence, and beyond.
Because I know you said it used to be done in 70, but...
Well, the problem that we're going to hit at the end of this chapter deals with parabolas. And earlier editions of the book tried to talk about translation, and that's been a little less the focus recently. I notice in later editions, what we've tried to do is some clever little work with getting the new vertex of the parabola. I remember yesterday we talked about taking a parabola and moving it over 1 and up 1. So in the same sense, if I start with this parabola, we know that that is centered at the origin, meaning the vertex, the low point of the parabola, is right at the origin. And if I move the vertex, so it's over 1 and up 1, we said that that equation is going to be y minus 1 equals x minus 1 quantity squared. We know exactly what the equation is going to look like. Well, if you write this in a non-simplified form, you have 1 plus x squared minus 2x plus 1. And so your equation is x squared minus 2x plus 2. This equation looks very different from here. This was standard form. And I can work from here backwards and get to this. So I would work this way. And now this tells me that if I go ahead and take my coordinate system again, And I want to know, where is this graph on this system that I'm saying, once I write it in this form, that I can simply go over 1, same thing I did before, up 1, so I'm going to set a new axis system and come over here 1. So this is my new axis system, big X, big Y. And I'm saying that if you want to go ahead and graph this, just go to the new system and treat it like it was y equals x squared, which means it'll be centered here. And it means if I go over 1 and up 1 this way, over 1 and up 1 this way, I'm going to have the parabola like it would usually look in standard form, graphed on the original system, xy. And so, again, referred to as a translation. And this is what we did in Math 70 and earlier editions. What's being done now is to look at an equation like this and say, well, where should the origin be? Where should the vertex be? Rather than completing the square. And I, again, am a very strong advocate of using completing the square to simplify process in a way that makes common sense rather than just learning a formula that you're going to say, well, I know where the vertex is going to locate. Just a comment, I added yesterday that we had a circle, then we set a parabola, then we argued we had 2 other curves. Now one of them I just used the more general notation oval rather than what?
Ellipse.
An ellipse. And then there is the hyperbola. Now what I didn't do, and I should have as I thought about this after the lecture yesterday, is sketching what those curves look like and give you a typical equation for each of them in standard form. And then I think you can see how nicely what we've talked about generalizes. Okay. I'm going to need to create a couple of lines here to make this look nice and neat. Okay, so let me try coming and making a box here for a moment. And I want to do it down here. Now what I'm going to do is create both the oval, called the ellipse, and the hyperbola in the process. Let's see, what do I want here? Yes, I want this up here. And this needs to come over. And I'm going to introduce a phrase that I just want you to be aware of. Boy, those don't look like I've done them the same distance, and I didn't. That was supposed to be out 1 more. Sorry about that. That didn't look like what I wanted at the end. Okay, I feel like I'm using the cloning tool in one of the packages. Now, what I've created is a little box here, and I'm going to put some dashed lines. Dashed lines up through here. These are 2 lines going through the origin. One is y equals x, the other is y equals minus x. Now, with that done, I'm going to get a branch like that, and this is called the hyperbola. Now, I haven't done justice to it as much as I'd like, but here's the argument. As you go out on this branch of the hyperbola, you never touch this dashed line I've drawn. Now, this line right here is going to be y equals x. Through the origin, slope 1. This line that I drew here is y equals minus x. So it is going through the origin with a slope of -1. these two lines are referred to as asymptotes. Meaning, the further you go out in the curve, the closer you get to the line, but you never touch it. You just get closer and closer and closer, but you never touch it. An asymptote. Now, what's the equation of that I just did? X squared minus y squared. We can't quite see the 1. Thank you. X squared minus y squared equals 1. Now that happens to be a hyperbola. Okay. Now what happens if I wanted to move that whole hyperbola over 3 and up 2? So I want to move the hyperbola just like I did the circle. What would you do? You'd say x minus 3 quantity squared plus y minus, not plus, negative y minus 2 quantity squared equals 1. Now that's that same hyperbola over 3 up 2. Okay. I want you to see what that equation would look like, thinking you work backwards. X squared minus 6x plus 9 minus y squared minus 4y plus 4 equals 1. I didn't plan that ahead well. Okay, and I know there's a problem picking that up. If you're in camera 2, I understand you can't tweak any more than that. So what I will do is just, let's see, what do I want to do there? Okay, just a moment. We'll get it so you can see it. This is going to be simplified. X squared minus 6x plus 9 minus y squared minus 4y plus 4 equals 1. Can we see that now? Yes. Then the next step, this would be x squared minus 6x. Notice minus y squared plus 4y, and then that would equal what? Well, the minus 4 and the plus 9 would be plus?
13. Or, I'm sorry.
Okay, you have a minus 4 and a plus 9 would be plus 5. Bring it over here, and that's going to equal negative 4. So if we started with something with both x squared and y squared in it, the difference is, notice here's a negative y squared. When it was a circle, it was a plus y squared. So you could work from here all the way back to here and say you have a hyperbola. Okay, that was the hyperbola. Now, what about the ellipse? This was the hyperbola here. The ellipse, and I'm just going to give you an equation for the ellipse because it's a little harder to do and I don't want to fight it. But let's say I had 4x squared plus 9y squared equals 36. Now if we just had x squared plus y squared equals 36, you would say a circle. What makes it an oval is that the coefficients of the x squared and the y squared are what? Different from each other. So what we actually do here, I'm going to divide everything by 36. Okay, we need to just a smidge. Thank you. Now, let's do x equals 0. If x is 0, y has to be plus or minus 2. Again, let's look at that. X is 0, so you're getting an intercept. Y is plus or minus 2. If y is 0, x is plus or minus 3. So you have something that going this way is plus or minus 3 from the origin. And going this way is only plus or minus 2 from the origin. So you have a little box that's 2 by the 3 away, and so you get like a rectangle, and you fit that curve inside the rectangle much as I had here, but the rectangle isn't a square, and you're going to get an oval. Now, that's standard form.
Which? The first one?
This one right here would be the standard form here, where you have it 1 on the right side.
Okay, so without moving it over, the standard form of an ellipse, if it was going to
This would be
origin,
centered at the origin
so
still.
it'd be x squared plus y squared equals 1, or
No,
would
x
definitely
squared
be a
over something squared plus y squared over something squared equals 1.
Okay. Ew, okay.
Okay, Ernie, I've run out of room, so we'll go over to the side with one of the cameras. And why don't I just, which camera are you on now?
Oh, 2.
It's okay, take one over there, and we'll just leave this up on the board. I'll walk over there, and we'll give you time to get those set differently in a moment.
Question mark. Squared.
Okay, we said x squared over 9, I think is what I have.
Yeah.
Okay, x squared over 9 plus y squared over 4 was equal to 1. Now, the argument was this is standard form. And what we're doing is saying this gave you, okay, if x equals 0, y equal plus or minus 2. If y is equal to 0, x is plus or minus 3. And so the argument was trying to do a coordinate system freehand.
Very good.
Not bad.
Okay, and then what I'm going to do is come up 2, down 2, 3 across each way. And so this creates a box. That didn't take as perpendicular as I wanted. Okay, let's see what that looks like. Okay. Then what we're going to do is just sort of fill in a smooth curve like this, and we'll come here in the same way. I don't know if that looks quite as smooth as I want. It looks like a racetrack a little bit, an oval. Now, that's centered at 0, 0. Now, what happens if I want this whole thing to just move over so it's centered at 3, 2? What do you think we would do if we're going to be consistent? Instead of having x squared, you'd have what? X minus 3 squared over 9 plus y minus 2 squared over 4, and that'll still equal what? 1. And that's just going to relocate that whole ellipse to a new center. Same idea. Now, I mentioned to you earlier, let's, okay, with camera 1, can you go back to my x squared minus y squared equals 1 on the front board for me? Okay, and whenever you're ready with that, Ernie, just do the switch. Okay, let's come back to that statement, because I wasn't really as fair with you as I should have been, because the question that was raised over here had to do with this being a standard form here, and then if we can come out just a little bit more, down to here, okay, and tweak maybe just a little bit more, because I need to see this from down here. There. This, we said, was a standard form, and it looks a little bit different from this. So, in a sense, if I had, instead of a plus sign here, a minus sign. So compare. And I'll get out of your way in just a moment. I hate it when that happens. Okay, I'll write it first, then I'll get out of your way. That will be, okay, a standard form for the hyperbola. Now, I had this as over 1, this is over 1. So that was x squared over 1 minus y squared over 1 equals 1. That's what allowed me to draw this box. Okay. If I do it here, my box is going to be a 3-2 box instead of a 1-1 box. Okay. And so it just changes how wide the hyperbola opens up. So, standard forms. Now let's go back to the sideboard, if you would, Ernie, with the camera. On what we have there, if I look at this general idea, we're going to now look at general forms. X minus h quantity squared over little a squared. Y minus k quantity squared over little b squared equals 1 is going to be an ellipse. It's understood that a and b are not the same. So a and b not equal. If I have x minus h quantity squared over a squared minus y minus k quantity squared over b squared, we're going to call this a hyperbola. A and b can be the same. So this was the ellipse. This is the hyperbola.
But those are the ellipse and hyperbola moved over to that other point,
right? HK. So if h and k are 0, at the origin, you just have x squared over a squared minus y squared over b squared equals 1. So at the origin, h and k are 0. Then I have x minus h quantity squared plus y minus k quantity squared equals r squared, and that's your circle. Again, if h and k are 0, you see the equations. And then finally, y minus k equals x minus h quantity squared, and that's the parabola. And so having an ellipse, a hyperbola, a circle, and a parabola in standard form can be adjusted and move it by having hk. So if h is 0, k is 0, you can see how quickly these simplify. So again, if h and k equal 0, what do we get? Well, we get x squared. I'll see if I'm going to keep those going. I have x squared plus y squared, this is over a squared, over b squared equals 1. There's your ellipse. Here, if h and k are 0, x squared over a squared minus y squared over b squared equals 1, you have your hyperbola. Here, you have x squared plus y squared equals r squared. You have your circle, and here you have y equals x squared, and these are considered standard forms before they are what? Moved, translated. If you want to move them to a new location, there is how you do it. Okay? And that is what's the same for those conic sections. And again, coming up to here, now, I've mentioned to you yesterday that content, traditionally, at least for the circle and the parabola down here, were part of what was in algebra. And just as an aside, when I've taught algebra in the past, I've just extended it to all 4 of these curves, because it is such a neat, easily done extension. All this based on what? Completing the square. So if we go back to the document cam and what triggers this, the statement that in number 4 was the quadratic formula, but in number 3 it was what? That completing the square is useful in other areas of mathematics. And that's what we just saw. These are the other areas of mathematics. Just so you have an idea of what content that talks about, it goes under the classification or the genre of analytic geometry. So analytic geometry. And it is the background that is very useful. And one of the things that has happened, to put some of this in perspective, with the advent of the graphing calculator, we have all too often said, just use the calculator, put in the equation, see the picture. This is a group of equations that should be part of your mental memory of equations and curves. So if somebody tells you later, here's the equations, x squared plus y squared equals 9. I would want you to have in your head that that's a circle. That it just pops into your head. If somebody says, I have x squared minus y squared equals 9, you know it's going to be a hyperbola. If somebody says, I have 4x squared plus 9y squared equals 36, you say, x squared and y squared have different coefficients. That makes it an oval or an ellipse. So, not necessarily that I want you to be in a position where you're graphing these, but more in a position I want you to recognize them. And that going on, that you're comfortable in working with those problems. Okay? So with that, let's talk about homework that you had questions on. And the first one I had questions from 19 and 21. So we are going to go back to section 10.2 and look at 19 and 21. Okay, Ernie, let's try 19. 4y squared plus 4y equals 3. Okay, we're going to have to be in camera 2, coming over here to the side. We want to solve this by completing the square. So I have 4y squared plus 4y plus 3 equals 0. This is number 19. And my direction, complete the square. What do I want to do first step?
Divide by 4.
I need a 1 in front of that y squared. So I'm going to divide by 4. So everything divided by 4. And of course what makes that uncomfortable is instead of having something nice as an integer, I get a fraction. So I have y squared plus y, and then I'm going to put this over here as negative 3/4. We need to add something to both sides so that the left side can be written as a what? A binomial squared. That's the argument. The coefficient of y is an understood 1. So we're supposed to divide that by 2. That's 1/2. And square that. Which is rather nice because I'm adding a 1/4 to a negative 3/4. It would have been a whole lot nicer if that had been a positive 3/4, correct?
Yes.
But it wasn't. So I have y plus 1/2 quantity squared equals negative 1/2.
Excuse me. Question.
Mm-hmm.
The original statement said, at least in my book, says 4y squared plus 4y equals 3.
Is that correct? Did I miswrite it?
Yes.
Let's go back to the text. I saw it as a plus 3, then this should have been what?
So it is a positive.
A minus 3. So this then would have become plus 3. Okay, so let's come to the side. So I should have had a negative 3 here, a plus 3 here. So we did luck out.
Get one.
That should be plus 1. And I completely misplaced erasers, so I need to pick up one and bring it back. So that's plus 1. Life is good. Otherwise, life was not good, because we would have had no solution in the set of reals. This is now good, because I have it with a positive over here. So we know y plus 1/2 is equal to plus or minus the square root of 1. That happens to be 1. So y plus 1/2 is equal to plus or minus 1. So we have two solutions. Y equals 1/2 plus 1, which is
Wouldn't it be negative 1/2?
negative 1/2 plus 1, thank you, which is 1/2. I'm getting careless with signs, it's obvious. And here I have y equals negative 1/2 minus 1. And so y is equal to negative 3/2. And I have my two solutions at 1/2 or negative 3/2. Okay, and I hope that answers the question that was asked online. Now let's go back to the text, because that was number 19. And so the question, we can't see 21 right there in the page. I'm going to have to scroll over to do that.
You might want to
So let me do that, and let's see how it differs. Sorry, the scroll had to stop momentarily. Ran out of space. There we go. So I have, in this case, 2p squared minus 2p plus 3. So I'm not sure how that is going to differ, but it was clearly a question. So let's carry that through. Number 21, I need to write it down first. And again, I have to be a little more careful here, because I need to make sure I write it correctly. I didn't get that done in the last equation. Now, let's come back, and will you examine to make sure I have that written correctly? We agree? The original problem?
p squared minus 2p plus, yes.
Okay, so I need to divide everything by 2 as my first step. So on the left side, I have p squared minus p, and on the right side, what? I do have the negative 3/2, and that's where I suspect I'm in trouble. Now, I need to know what can I add here and here so that on the left side I have a perfect square. So we're going to do what again? The coefficient understood here is a negative 1. I divide that by 2 and square it, so that's going to be a 1/4 I add there and a 1/4 I add here. Now, when I had done that originally, I think if I go back, and what I'm going to, let's slide over just a moment, Ernie. I was a little bit messy with what I had done here. If I had gone ahead and made that as a 2 there, it wouldn't have looked as cluttered, and instead of the 1/4 here, I could have what? Treated that as 1/4, and I think that would have looked a little bit nicer than what I did. With that in mind, now we'll slide back. Same idea here. So on the left side, I now have p minus 1/2. Notice the negative sign this time, squared. And that's equal to, okay, this is going to be negative 9/4. No, Pearl, I was squaring, I shouldn't have been squaring. 6/4. Ah, negative 6/4. And I want what? Plus 1, which is negative 5/4 when I get done? I've been squaring too many numbers in my head. Okay, so we have negative 5/4, so are we in agreement there?
Mm-hmm.
Now the problem I have when I take the square root of both sides.
negative within there.
And I'm going to do this in a quotient form this way, because I can take the square root of 4, so I have p minus 1/2 is equal to plus or minus the square root of, I want that minus sign to be a little bit separated, the square root of negative 5 over 2. And I'm still going to carry that out one more step where I have p is equal to 1 plus or minus the square root of negative 5 over a common 2. So we need to tweak just a smidge in that, Ernie. Thank you. Now the square root of minus 5. Not in the real numbers. However,
Right now, it's not a real number.
all right, okay, but it's going to be very soon a what?
Imaginary.
Well, first, a complex number, because we are going to argue that the square root of negative 5 is rewritten as the square root of negative 1 times the square root of 5, and we are going to define a new term called little I for imaginary. And say we have I, the square root of 5. So if, big if, that is the case, then we could argue that p is equal to 1 plus or minus I, the square root of 5 over 2, and we now have extended our solutions to the complex numbers, because ultimately we are wanting, notice the royal we, everybody included, we want two solutions to a second degree equation, known as a quadratic equation. So the degree should be the same as the number of solutions. That's what we want in mathematics. To achieve that, we create a new number system to make it happen. Again, as I said yesterday, this is in the same spirit of over 2,000 years ago, where we said we would like to be able to measure the diagonal of a square. And we had to create a new number to do it, called an irrational number, meaning it could be written as a ratio. Not that it wasn't rational in the sense of rational thought. And imaginary doesn't mean it's a figment of our imagination. It just means a new number that allows us to have two solutions to a second degree equation, which was a result of some work by Gauss. I think Gauss is with two S's. Carl Friedrich Gauss. And he, at the tender age of 18, got his doctorate. And one of the fundamental arguments was precisely this, that an nth degree equation should have n roots, n solutions. And in order to do that, you need the complex numbers. Okay? So that's all related to the process. Let's go back to the document, Cam, to the problem we were looking at. That was 21.
So the solution to that one in
In
this
the real
text,
numbers is, of course, the question that's being asked.
the empty sign.
If you have, and 21 is we saw it, and you were answering the question for this set of problems, then the answer is yeah, we had no solution because we were in the set of reals and we had the square root of a negative, and that's not possible. However, if we extend our number system, as we just did, which is another section of the chapter, we would have two solutions and life would be good. In case there is some disbelief as to what we are doing, I just want you to note on page 599, moving ahead gently, the complex numbers on 599. Okay. And indeed, as we come off there for a moment, Ernie, I have to give some credibility to what I'm doing here. Near the midpoint, or at least 1/3 down on the page, hence the good use for a fraction 1/3 down. I is the square root of minus 1, and I squared is negative 1. So that's what we are going to define as a way of extending the number system. Okay.
Couldn't you have saved the imaginary number for next semester? It would have been
I've been
so
asked if I could have,
nicer.
in an imaginative way, saved the imaginary numbers for next semester. No. Because we want you to be introduced to the imaginary numbers so the next time you meet them, you say, a deja vu moment. I've seen them before. Okay, so we're looking ahead for your welfare.
Okay. God, I'm so glad you.
Are there any other questions on the homework from last night? We covered 2 of them that were asked.
I had a lot of difficulty with homework last night. I don't know why I had it, but I did.
Problems with the homework and completing the square? Is that
I thought that
something you
I
want
don't
to
know.
make specific, or is that just a general statement?
General statement, because yesterday in class, we went over completing the square and the quadratic formula.
Mhm.
So I was plugging in the quadratic formula for everything.
Oh, you were using the
Did last
quadratic
time.
formula and shortcutting completing the square.
And I was,
That's not cool.
no, and I came up with way different answers, so.
Well, they look differently perhaps, but if you simplify your answers with the quadratic formula,
Would it come out the same?
they should look like twins.
Oh, I didn't take it that far.
Okay, but
I
that
was
would
very
be, I
frustrated
think...
when I was looking at the, I was
Okay,
thinking, that's not
sorry.
looking.
But one of the other things I ask you to do is illustrated in this process on page 590, where we take a quadratic equation and generate it to what? The quadratic formula. I just want to bring it to your attention that what we were doing in the board before is all carried through there. Okay? So, this brings up the question. Michelle's comment about just doing the quadratic formula and having them not look the same. And that's very true. If you start out with completing the square and you carry it through and then you plug into the quadratic formula and compare your results, they aren't going to look the same, but you can demonstrate they're the same as you simplify your expressions. They should come out looking exactly the same at the end. Now, before I make a comment here, I'm trying to decide what I want to do. Were there any other questions about the homework? So if we completed the square, things were cool. But if we used the quadratic formula, they didn't look quite the same. Okay, I've got it. And I'm also down to no time. Okay, what kind of activities can we have you do for this evening?
Just the examples.
No, what I have in mind is coming back to the homework from last night, which was 10-2, right?
Mm-hmm.
Yes.
And we had problems which were, for example, starting with 13. Let's look at that for a moment. Number 13. I'm going to ask Michelle a question. If we did number 13, and you want to use the quadratic formula, what would you have to do to that?
Well, first I would take that 4 and pull a divide by 2 and square
Oh, so you
it.
did square that and
Yes.
added 4 to both sides.
I did.
So you didn't just use the quadratic formula.
Well,
Because what would you have to do if you were to do the quadratic formula? This is what I was trying to get at. Let's come back one more time, Ernie.
or did I just...
I would have to take x squared minus 4x plus 3 equals 0 to use a quadratic formula. I'd have to simplify it so that we had 0 on the right side.
Okay, I did that. To use the quadratic formula,
Yes,
right?
but to do it by completing the square, I didn't have to make that as a first step. So coming off there, I'm confused now, Michelle.
I pulled it all over to one side.
And then use
Made
the
it
quadratic
0.
formula.
Yes.
That's what I thought you were telling me. But then you said you took 1/2 of 4 and squared it.
Yeah, and then I pulled it down and
Are you at
did the
13?
minus b plus or minus
Okay,
the square root
gotcha.
of...
Okay, now I understand. Let's come back to the problems. There's the problem that we were just talking about. Now, number 16 is in the form it needs to be, but we did odds, is that correct? So let me come off there for a moment, Ernie. Let's look at 17. Okay, here's 17. It's been set up appropriately for you. Let's come off there. I'm still hunting for problems that haven't been set up well for you. 23. What would you do in your first step in 23? You bring the 4 to the left side, set it equal to 0, and then proceed. So here's what I want you to do for homework. You did the problems by completing the square. You did them on in the ones that we're talking about, 13 through 27 odd, right? I'd like you to redo those now using the quadratic formula on the same set and compare your answers. Then we'll give you another evening with the same, so you know what your solutions were before. So what I'm saying here, I'm going to take each problem such as, an example, here's 23 again. Your first step will be what? To bring the 4 on the left side and rewrite it as 3k squared plus 7k minus 4 equals 0. So A is 3, B is 7, C is minus 4. Then you're going to substitute into the quadratic formula and solve. Get your answer and compare to what you did last night. They should look the same when you're done.
Okay, so everyone does that but Michelle, and she does completing the square.
Everything Michelle does now is last night's homework. We're completing the square. So you're all going to end up at the same spot at the
I
end.
need to take my homework home.
Okay, so nobody's turning in anything. You just repeat, but now use the quadratic formula. And oh, by the way, I want you to again practice starting with ax squared plus bx plus c equals 0 and get to the quadratic formula. And we'll continue this process tomorrow. Ernie, we close with the doors. And your selection?
The doors.
But what's the song?
The end.
No, that's not a good one because it'll just go nothing. So maybe how about break through to the other side? So we'll do break through to the other side and have a great day.